All right. Hello, this is Leo, and I'm Noah. We're going to be telling you about what harmonic motion is and some examples of it in real life. So, Leo will get us started.
So harmonic motion is the concept that a given object moving between 2 points, the maximum and the minimum, with a smooth take on it.
Okay, so now whenever you will see harmonic motion, we said it has to be smooth. So we'll model it like by a sine wave or cosine wave, and the reason why we have to model it as a curve is because one of the elements that is required for motion to be harmonic is that as an object drifts away from its starting point to one of the two maximum or minimums that we named, a force will try to be pushing it back to its original point, and the force gets stronger the farther away it gets. So there will come a point as it's getting closer to the maximum or minimum that the force will get stronger. It will slow down the object until it will stop and then move back. It'll slow down again, then move back, and so we model it by a curve instead of a jagged line, which would just be one object colliding off of two back and forth and back and forth.
So piggybacking off what my colleague Noah has said, now this harmonic motion can be identified as a sine or cosine wave with this graph. The x-axis would represent the amount of time it would take for it to complete its full cycle or whatever it is. And then the y-axis would say its maximum and its minimum, all in the meantime in between these 2 points colliding.
Okay, so now we're going to give you a few examples of what harmonic motion could look like. So first over here, we have what would be a ball or a weight on a spring. Now, right at rest, the spring would, or the ball would sit right here. If we stretched it down to this level, to its minimum, and then we let it go, it would slowly speed up and hit here and be moving its fastest, and it would come back up to the top and compress the string. And this would be its maximum. Then the force of the string will push it back down. Then the stretch of the spring will push it back up. And this is how this was shown as harmonic motion. Over here, we have a drawing of a pendulum. If we started the pendulum up here at the top, gravity will drop the pendulum to its bottom, and then its own speed or kinetic energy will carry it back up to the top, and then it will come back up, and then down, and then up again. And then finally, with the graph that we have on the board here, this is our two waves. Each of them, or the bottom one here, is describing all of the different sunrise times in Salt Lake City, Utah, over the course of 1 year, and up here are those sunset times of the same day. This is shown as harmonic motion because the points will change over time as the Earth is oriented differently with the sun. So, and you see that it follows the same cosine or sine wave that harmonic motion will follow. That's why this itself is harmonic motion.
Yeah. Now, what we have said before is that these graphs, when you graph in the sine or cosine, it shows certain variables, that's the incorrect term, of normal graphs. One of those variables is the amplitude. As we have stated before, the amplitude is the maximum part of the graph and the minimum part of the graph.
So what we see in the different graphs is that, so we see the amplitude is the distance between the start and the maximum and the minimum. So in this case, it would be where the ball starts and where it either ends here on the bottom or ends here on the top. With the sunset or sunrises, it would be down here at the bottom or the top, which would tell us the earliest time the sun rises or the latest time the sun sets, or vice versa for each. And finally, for the pendulum, the distance it would go from its top and then sitting straight down, that's our amplitude.
Another aspect of this graph is the period. Now, the period is how long it takes for whatever cycle it is, from ball on a string or a pendulum, or a sunset or sunrise, to reach its full cycle and go back to the zero of it, as shown here. So from this 0 point to this next point, this is all one period.
So we would see with the spring, as it goes down, it'll come back up and then finally come back to its starting point, and that's one period. At the pendulum, we see that it will go down to its bottom point, come back up, go down again, then start to the original. That's one period. And then finally, for the course of our sunsets and sunrises, as the Earth goes around the sun, once it's come back at the same time of year, we'll have made one complete revolution, and the points will be back where they started, in which case our period would be 1 year.